The implicit function theorem is one of the central results of multivariable calculus and differential topology. Its scope extends from clean analytical statements about smooth maps between open subsets of Euclidean space all the way to structural theorems about embedded submanifolds. This presentation works through the complete logical chain. It begins with the contraction lemma and moves through the inverse and implicit function theorems in Euclidean space. From there, it reaches the rank theorem and the level set theorems that constitute the manifold-level content of the implicit function principle. Every result in this presentation sits in a strict logical hierarchy. The foundation is the contraction lemma, a fixed-point theorem for complete metric spaces. From it, one derives the inverse function theorem in Euclidean space. If the total derivative of a smooth map is invertible at a point, the map is locally a diffeomorphism there. The implicit function theorem then follows by reducing the implicit equation problem to an application of the inverse function theorem. The rank theorem, which is the nonlinear canonical form theorem for smooth maps of constant rank, uses the inverse function theorem on manifolds, itself inherited from the Euclidean version. At the top of the chain sit the level set theorems, which are the geometric content of the implicit function principle in the category of smooth manifolds. A contraction on a metric space X is a self-map G from X to X that uniformly shrinks distances by a fixed factor strictly less than 1. Precisely, there must exist a constant lambda in the open interval from 0 to 1, the contraction constant. For every pair of points x and x prime in X, the distance between g of x and g of x prime must be at most lambda times the distance between x and x prime. A fixed point of g is a point x in X satisfying g of x equals x. The contraction condition forces G to bring all pairs of points strictly closer together, which is the mechanism that produces a unique fixed point. A contraction G on a metric space acts on every pair of points simultaneously. The number line here carries 5 points at distinct positions. They represent arbitrary points of X. The contraction constant lambda is set to 0.6, meaning G must bring every pair of points to within 60% of their original separation. The brackets above the number line measure two representative pairwise distances before any application of G. These are the distances d of x and d of x prime for the two selected pairs. Every application of G must multiply each such distance by at most lambda uniformly for every pair, not merely on average. After one application of G, the new positions appear as smaller dots. The brackets below the line measure the new distances d prime for the same two pairs. The ratio d prime over d equals 0.6 in both cases. G shrinks every pair by exactly the factor lambda. The uniformity is the content of the contraction condition. It is not sufficient that G shrinks some distances. It must shrink all distances by a uniform factor strictly below 1. Three further applications of G drive the 5 points into a progressively tighter cluster. Each iteration multiplies all pairwise distances by lambda, so after k applications, the distances have shrunk by a factor of lambda to the k. Since lambda is less than 1, lambda to the k tends to 0 as k grows, forcing the entire orbit to converge to a single location. The fixed point of G is the unique location every orbit converges to. It satisfies G of x star equals x star by construction. Its image under G is itself. The shrinkage visible here is the geometric mechanism behind the contraction lemma. The orbit is automatically Cauchy because consecutive distances decay geometrically, and completeness of X turns this Cauchy property into convergence. The contraction lemma asserts that on any non-empty complete metric space, every contraction has a unique fixed point. The two hypotheses power the two halves of the conclusion. The contraction bound alone forces uniqueness, no completeness needed. Completeness guarantees that Cauchy sequences converge, which is what produces existence. Both halves are proved in full on the next slides. The contraction lemma constructs the fixed point by iteration. Fix any starting point x0 in the complete metric space X, no constraint on where x0 sits. Define x sub n plus 1 to be g of x sub n for each n. The fixed point x star is not given in advance, it is produced by the orbit. One application of G produces x sub 1. The bracket d0 shows the initial distance from x0 to x sub 1. The contraction bound gives d of x sub 1 and x sub 2 at most lambda times d0. Each step reduces the distance to the next iterate by the factor lambda. Iterating further produces x2, x3, and x4, with successive distances decaying by the factor lambda at each step. The bracket labels show d0, lambda times d0, lambda squared times d0, and lambda cubed times d0. This geometric decay is what will make the sequence Cauchy. The triangle inequality estimate is carried out on the existence slide. Further iterates x5 through x8 crowd into a tight cluster. The sequence is Cauchy, the pairwise distances become arbitrarily small, but no limit point is visible on screen yet. Completeness of x is the axiom that guarantees such a Cauchy sequence converges to some point in x. Without completeness, the limit might not exist in the space. The fixed point x star materializes as the limit of the orbit. Completeness produced it from the Cauchy property of the sequence. X star was not postulated, but constructed. The cluster of iterates collapses to the single point, and the proof identifies it as the fixed point by invoking the continuity of g. G of x star equals the limit of g of x sub n, which equals the limit of x sub n plus 1, which is x star. The equation g of x star equals x star confirms that x star is a fixed point. The formal proofs of uniqueness and existence follow on the next two slides. The orbit seen here will return as the surjectivity mechanism in the inverse function theorem. To establish uniqueness, suppose x and x prime are both fixed points of g, then d of x and x prime equals d of g of x and g of x prime, because x equals g of x and x prime equals g of x prime. The contraction bound then gives d of g of x and g of x prime is at most lambda times d of x and x prime. Combining these, d of x and x prime is at most lambda times d of x and x prime. Since lambda is strictly less than 1, rearranging gives 1 minus lambda times d of x and x prime is at most 0. Because 1 minus lambda is positive and d of x and x prime is non-negative, d of x and x prime must equal 0, hence x equals x prime. Uniqueness follows. For existence, fix any point x0 in x and define the sequence x sub n inductively by x sub n plus 1 equals g of x sub n. Applying the contraction bound once gives d of x sub 1, and x sub 2 is at most lambda times d of x0 and x1. By induction, the distance between consecutive terms decays geometrically. D of x sub I and x sub I plus 1 is at most lambda to the I times d of x0 and x1. To show the sequence is Cauchy, take integers j greater than I at least n, apply the triangle inequality over the telescoping sum of consecutive distances, and bound by the geometric series. The result is d of x sub I and x sub j is at most lambda to the n over 1 minus lambda times d of x0 and x1. As n grows, this tends to 0, so the sequence is Cauchy. Completeness of x then guarantees convergence to some point x. Every contraction is continuous. The Lipschitz condition with constant lambda less than 1 is stronger than continuity. Therefore, g of the limit equals the limit of g of x sub n, which equals the limit of x sub n plus 1, which equals x. So x is a fixed point. Combined with uniqueness, this completes the proof of the contraction lemma. The fixed point machinery established here is what drives the surjectivity argument in the inverse function theorem. The inverse function theorem addresses the local invertibility of a smooth self-map of Euclidean n space. The hypothesis is that the total derivative, the Jacobian matrix, of f is invertible at a particular point A. Invertibility of a linear map from Rn to Rn is equivalent to its determinant being non-zero, so the condition is checkable. The conclusion is that there exist connected open neighborhoods, u0 of A in the domain, and v0 of f of A in the codomain. The restriction of f to u0 is then a smooth bijection from u0 onto v0, whose inverse is also smooth, a diffeomorphism. The theorem is purely local. It makes no claim about f outside u0. The proof begins with a normalization that simplifies the algebra without loss of generality. First, translate so that the base point is the origin. Define f1 of x to be f of x plus a minus f of a. Then f1 maps 0 to 0, and its derivative at 0 equals df of a, which is still invertible by hypothesis. Second, precompose with the inverse of df1 of 0 to normalize the derivative. Define f2 to be df1 of 0 inverse, composed with f1. Then df2 of 0 is the identity matrix I sub n. This is the normalization we carry through the rest of the proof. F maps 0 to 0 with derivative equal to the identity. The determinant of df of x is a continuous function of x, and after normalization it equals 1 at 0. We may therefore shrink u to ensure df of x is invertible at every point of u, not merely at the origin. This will be used in later steps. Define h of x to be x minus f of x, the deviation of f from the identity. Since df of 0 is the identity, dh of 0 equals 0. By continuity of dh, there exists delta greater than 0 such that the operator norm of dh of x is at most 1/2 throughout the closed ball of radius delta around 0. The mean value inequality then gives a Lipschitz bound. H moves any 2 points in that ball by at most 1/2 of their mutual distance. Injectivity follows from this Lipschitz bound. Write x prime minus x as f of x prime minus f of x plus h of x prime minus h of x. The second term is at most 1/2 of the norm of x prime minus x. Rearranging then gives that the distance between x and x prime is at most twice the distance between f of x and f of x prime. If f of x equals f of x prime, then x equals x prime. F is injective on the closed ball. For surjectivity onto the half-radius ball, fix any y in b delta over 2 of 0 and define g sub e of x to be y plus h of x. A fixed point of g sub e satisfies x equals y plus h of x, which rearranges to f of x equals y. For x in the closed delta ball, the norm of g sub I of x is at most the norm of y plus the norm of h of x. That sum is less than delta over 2 plus 1/2 of the norm of x, hence at most delta. So g sub e maps the closed delta ball into itself, and its Lipschitz constant is 1/2, so it is a contraction. The contraction lemma then guarantees a unique fixed point x, the unique preimage of y under f. The surjectivity step in the inverse function theorem proof constructs, for each target point y, a preimage under f by applying the contraction lemma. 2 concentric balls appear, the closed delta ball is the domain of the contraction, and the open half-radius ball is the target neighborhood whose points will be shown to lie in the image of f. Fix any target point E in the half-radius ball. The surjectivity argument must produce an x in the delta ball with f of x equal to y. The strategy is to express this as a fixed point problem. Define g sub e of x to be y plus h of x, where h of x equals x minus f of x, then g sub e of x equals x is equivalent to f of x equals y. The arrow shows the containment property, the estimate from the previous slide, norm of y below delta over 2, plus the Lipschitz bound on h, keeps g sub e of x strictly inside the delta ball, so g sub e maps the closed ball into itself. The brackets show the second ingredient, the y term cancels in g sub e of x prime minus g sub e of x. The Lipschitz half bound on h then makes g sub e a contraction with constant 1/2 on the complete closed ball. The contraction lemma applies. The contraction lemma delivers a unique fixed point x star of g sub e in the delta ball, and g sub e of x star equals x star rearranges to f of x star equals y. The loop at x star is that fixed point equation made visible. Every y in the half-radius ball is hit, which is the surjectivity claimed on the previous slide. Step 3 establishes the open neighborhoods. Set v0 to be the open half-radius ball, and u0 to be the intersection of the open delta ball with the preimage of v0 under f. Being an intersection of 2 open sets, u0 is open. Since v0 is connected and f inverse is continuous, as the injectivity estimate gives a Lipschitz bound for f inverse, u0 is also connected. The restriction of f to u0 is a continuous bijection onto v0. Step 4 establishes differentiability of f inverse. Fix E in v0 and let x equal f inverse of y and L equal df of x. For y prime near y, set x prime equal to f inverse of y prime. The difference quotient for f inverse can be bounded using the injectivity estimate, which shows the ratio of the norm of x prime minus x to the norm of y prime minus y is bounded above. As y prime tends to y, x prime tends to x by continuity of f inverse, and the remainder in the definition of differentiability of f at x tends to 0. Hence f inverse is differentiable at y, with derivative equal to the inverse of df at f inverse of y. Step 5 proves that f inverse is smooth by induction on the order of differentiability. The formula for D of F inverse expresses it as a composition of three maps, F inverse, then the Jacobian map, dF, then matrix inversion. Matrix inversion is smooth on the general linear group by Cramer's rule, which expresses the entries of the inverse via polynomial cofactors divided by the determinant. If F inverse is Ck, then D of F inverse is a composition of Ck maps with smooth maps, hence Ck, so F inverse is Ck plus 1. Inducting, F inverse is smooth. The inverse function theorem is proved. The contraction argument required to produce the local inverse will reappear in the proof of the implicit function theorem, where the same surjectivity mechanism is used in a higher dimensional setting. Two corollaries of the inverse function theorem are immediate. First, if the Jacobian determinant of a smooth map F from an open set U in Rn is non-zero at every point of U, then F is an open map. The argument is that around every point A, the inverse function theorem provides a local diffeomorphism onto a neighborhood of F of A, so F of A is interior to F of U. Since A was arbitrary, every image point is interior, meaning F of U is open. Second, suppose F is also injective, a smooth bijection from U onto its image. Then the inverse F inverse exists globally on F of U and agrees locally at every point with the smooth inverse guaranteed by the inverse function theorem. Local smoothness is sufficient for global smoothness, so F inverse is smooth, and F is a diffeomorphism onto its image. The implicit function theorem solves the following problem. Given a smooth equation phi of x and y equals c, when can the solution set near a particular point be written as the graph of a smooth function y equals f of x? The setting is a smooth map phi from an open subset of Rn times Rk to Rk. The variables are split into x in Rn, the free parameters, and y in Rk, the variables being implicitly defined. The hypothesis is that the k by k matrix of partial derivatives of phi with respect to the y variables alone, evaluated at the base point a and b, is non-singular. This is an invertibility condition on the y Jacobian only, with no assumption on the x partial derivatives. The conclusion is that around a and b, the level set phi inverse of c is exactly the graph of a smooth function f from v0 to w0. Every solution of phi of x and y equals c near a and b has the form x and f of x for a unique smooth f. The key mechanism in the proof is that phi can be embedded into a square map via the auxiliary construction psi of x and y equals x and phi of x and y. The inverse function theorem then inverts psi locally, and the implicit function f is extracted as a component of the resulting inverse. Without the hypothesis that the y Jacobian is non-singular, the level set near a and b may fail to be a graph, it can be tangent to the x fibers or develop singularities. The proof constructs the psi map and applies the Euclidean inverse function theorem to it, which requires examining the block structure of d psi. The implicit function theorem operates in the product space Rn times Rk for this two-dimensional illustration, that is the xy plane. The level curve of a smooth function phi of x and y at a fixed value c is the set of all points where phi equals c. The theorem answers the question of when this level curve can be expressed as the graph of a smooth function y equals f of x. The S-shaped curve is the full level set phi of x and y equals c. Globally, this curve is not the graph of any function of x. The vertical dashed line at the indicated x value meets the curve in three distinct points, showing that x alone does not determine y. The level set has a fold, a region where the y partial derivative of phi vanishes and the curve turns back on itself. The implicit function theorem is a purely local result and does not require the level set to be a global graph. Choose a base point a and b on the monotone piece of the curve, where the curve is locally the graph of a function. At this point, the y partial derivative of phi is non-zero, the curve is not turning back on itself, and the hypothesis of the implicit function theorem is satisfied. The theorem produces a product neighborhood v0 times w0 around the base point a and b. Within this box, the level set has a specific structure. It coincides with the graph of a smooth function f from v0 to w0. Outside the box, the level set may fold or branch. The theorem makes no claim about the global structure. Inside the box, the highlighted piece of the curve is the graph of a smooth function. Each x value in v0 determines a unique y value f of x in W0, shown by the vertical dashed lines from the x-axis to the curve. The fact that these vertical lines meet the curve in exactly one point, rather than 2 or 0, is the geometric content of the non-singular y-Jacobian hypothesis. The curve is not tangent to the x direction at a and b. The identity phi of x and f of x equals c holds throughout V0. Every point on the graph of f lies in the level set. The converse, that every point of the level set inside the box lies on the graph of f, follows from the uniqueness part of the implicit function theorem. That uniqueness is itself a consequence of the injectivity of the local inverse of psi constructed in the proof. The proof constructs an auxiliary map psi from U to Rn times Rk by psi of x and y equals x and phi of x and y. This embeds phi into a map whose domain and codomain have the same dimension n plus k, making it a candidate for the inverse function theorem. Computing the total derivative of psi at a and b, one finds a block lower triangular matrix. The upper left block is the n by n identity coming from the x component of psi. The lower right block is the k by k matrix of partial derivatives of phi with respect to y, the matrix assumed non-singular by hypothesis. A block lower triangular matrix with invertible diagonal blocks is itself invertible. Its determinant is the product of the diagonal block determinants. Since d psi at a and b is non-singular, the inverse function theorem applies to psi. There are connected open neighborhoods on which psi is a diffeomorphism. Shrinking to a product neighborhood v times w, the local inverse psi inverse exists and is smooth. Write psi inverse of x and y as a of x and y in Rn and b of x and y in Rk. Composing psi with psi inverse and comparing the first component gives a of x and y equals x for all x and y in the image. So psi inverse takes the simpler form x and b of x and y. Setting f of x equal to b of x and c, the identity phi of x and f of x equals c holds throughout V0. The graph of f lies in the level set. The converse, that every solution in V0 times W0 has the form x and f of x, follows by applying psi inverse. If phi of x and y equals c, then psi of x and y equals x and c. So x and y equals psi inverse of x and c, which equals x and f of x. The implicit function is smooth because B is a component of the smooth map psi inverse. The auxiliary map psi sends a point x and y in Rn times Rk to x and phi of x and y. Its total derivative at the base point a and b is a block matrix of size n plus k by n plus k. The upper row comes from differentiating the x component of psi, which is the identity map on Rn. The lower row comes from differentiating phi. The upper left n by n block is the identity matrix I sub n, contributed by the x component of psi. This block is trivially non-singular. Its determinant is 1. It appears because psi passes the x variables through unchanged. The lower right block is the y-Jacobian of phi, non-singular by hypothesis. With both highlighted diagonal blocks invertible, the block triangular determinant argument from the previous slide makes d psi invertible, and the inverse function theorem applies to psi. The flow diagram shows what psi does to a point x and y. The x component passes through psi unchanged, emerging as the first n components of the output. The y component is transformed to phi of x and y. The output is therefore x and phi of x and y, which we label x and z, where z equals phi of x and y. Because psi is a local diffeomorphism near a and b, the map psi inverse exists and is smooth on a neighborhood of a and c, where c equals phi of a and b. Slicing at z equals c extracts the implicit function f of x equals b of x and c, the second component of psi inverse along the dashed slice. The identity phi of x and f of x equals c, verified on the previous slide, is now visible as the flow through the diagram. Since phi of x and f of x equals the constant c, differentiating both sides with respect to x using the chain rule gives a system of equations. In the ith row and jth column, the partial derivative of phi I with respect to xj plus the sum over L of the partial derivative of phi I with respect to yl times the partial derivative of fl with respect to xj equals 0. This is the total derivative of the composition evaluated at 0. Solving for df of x, the y partial derivative matrix times df equals the negative of the x partial derivative matrix. The y partial derivative matrix is invertible by the hypothesis of the theorem, and it remains invertible throughout V0 by continuity and shrinking. One can therefore multiply on the left by its inverse to isolate df. The result is df of x equals negative, the inverse of the y Jacobian times the x Jacobian, both evaluated at x and f of x. This formula provides an explicit recipe for computing the derivative of the implicitly defined function f without first solving for f analytically. The smoothness of f is a consequence of the smoothness of psi inverse, established in the inverse function theorem proof, and does not depend on this differentiation formula. The rank theorem, which requires controlling the Jacobian of a map of constant rank, will draw on the same inverse function theorem machinery used here. Before stating the rank theorem, two definitions establish the vocabulary. The rank of a smooth map f between smooth manifolds at a point P is defined as the dimension of the image of the differential df at P. Equivalently, it is the rank of the Jacobian matrix in any smooth chart. The chart independence of rank follows from the fact that changing charts multiplies the Jacobian on both sides by invertible matrices, which preserves rank. F has constant rank R if this dimension is the same R at every point of M. An immersion is a smooth map whose differential is injective everywhere. The tangent map never loses information. For a map from an M manifold, this requires the rank to equal M everywhere, so M must be at most N. A submersion is a smooth map whose differential is surjective everywhere. The tangent map hits the entire target tangent space. For a map from M to N, this requires the rank to equal the dimension of N everywhere, so N must be at most M. Both conditions imply constant rank, which is the hypothesis of the rank theorem. The rank theorem is the nonlinear analog of the canonical form theorem for linear maps. Any linear map from Rm to Rn of rank R can be put into the standard projection form by independent changes of basis in domain and codomain. The rank theorem replaces changes of basis with smooth coordinate changes, diffeomorphisms on the domain and codomain manifolds, and achieves the same canonical form for any smooth map of constant rank. The canonical form maps x1 through xr to x1 through xr and all remaining coordinates to 0. In appropriate coordinates, a constant rank map is exactly a projection. Two special cases are worth naming. A smooth submersion, where the rank equals the dimension of n, looks in coordinates like projection onto the first n factors. The last m minus n coordinates of the domain are simply discarded. A smooth immersion, where the rank equals the dimension of m, looks like inclusion into the first m coordinates of the codomain. The image sits in the coordinate slice where the last n minus m coordinates are 0. The rank theorem guarantees that every smooth map of constant rank R between manifolds can be written in the canonical projection form in appropriate coordinates. This visual shows the coordinate straightening process. The domain open set U in Rm and the codomain open set V in Rn are connected by a smooth map F of constant rank R. In the standard coordinates shown, F is curved, it does not look like a projection. The first coordinate change phi acts on the domain. It is a local diffeomorphism near the base point constructed using the inverse function theorem, and it straightens the first R components of F to the identity map on RR. After precomposing with phi inverse, the map F composed with phi inverse sends x and y in RR times Rm minus R to x and R tilde of x and y, where x passes through unchanged. The second coordinate change psi acts on the codomain. It is defined by psi of v and w equals v and w minus s of v, where s of x equals r tilde of x and 0. This subtracts the s contribution from the last n minus r components, eliminating the dependence on x in the lower block. After post-composing with psi, the composite map psi composed with f composed with phi inverse sends x and y to x and 0. In the new coordinates provided by phi on the domain and psi on the codomain, the map F becomes the canonical projection, sending x and y to x and 0. The curved arrow is replaced by a straight horizontal arrow, and the w-axis in the codomain is crushed to 0. The last n minus r components of every image point vanish. The two independent coordinate changes, one on each side, together transform an arbitrary constant rank map into the simplest possible form. In the canonical coordinates, consider the level set of F at the value C, the set of all points mapping to C and 0. It is the slice where the first R coordinates are fixed at the value determined by C, and the remaining m minus r coordinates are free. This slice appears as a vertical line in the two-dimensional illustration. The constant rank level set theorem follows, asserting that every level set, in the canonical coordinates of the rank theorem, is a coordinate slice of codimension R, a properly embedded submanifold. The proof is local, via charts. Replace M and N by open subsets of Rm and Rn with P at the origin. Since df of 0 has rank R, its matrix has some R by R minor with non-zero determinant. Permuting the domain and codomain coordinates, assume this is the upper left block, indexed by the first R domain and first R codomain indices. Write the domain coordinates as x in RR and y in Rm minus R, and the codomain coordinates as v in RR and w in Rn minus R. Decompose f into its first R components q and its remaining n minus R components R. Define the domain change of coordinates phi of x and y to be q of x and y and y. The first R components are replaced by the q values, and the last m minus R components are kept unchanged. The derivative of phi at 0 is block upper triangular. The upper left block is the x Jacobian of q, which is non-singular by assumption, and the lower right block is the identity of size m minus r. These two blocks together determine the determinant, hence d phi at 0 is non-singular. The inverse function theorem then gives that phi is a diffeomorphism near 0 onto an open cube u tilde 0. Write phi inverse of x and y as a of x and y in RR and b of x and y in Rm minus r. Composing phi with phi inverse and comparing the second component forces b of x and y to equal y. So phi inverse of x and y equals a of x and y and y. Substituting into f, one finds f composed with phi inverse of x and y equals x and r tilde of x and y, where r tilde is the composition of r with phi inverse. The first r components of f have been straightened to the identity. Step 3 uses the constant rank hypothesis to show that r tilde of x and y is independent of y. Compute the Jacobian of f composed with phi inverse. By the chain rule, the top left r by r block is the identity, and the top right r by m minus r block is 0. The bottom left is the partial derivative of r tilde with respect to x, and the bottom right is the partial derivative of r tilde with respect to y. Composing with the diffeomorphism, phi inverse preserves rank everywhere, so this Jacobian has rank r throughout u tilde 0. The first r columns are already linearly independent, they form the identity block. For the total rank to remain r and not exceed it, the remaining columns must contribute 0 to the span, which forces the partial derivatives of r tilde with respect to y to vanish identically. Because u tilde 0 is a cube, each vertical slice, the set of points with a fixed x, is a connected segment, and a function with 0 y gradient is constant along each such segment. So r tilde is independent of y on all of u tilde 0. Define s of x to be r tilde of x and 0. Step 4 straightens the codomain. Define the codomain. Coordinate change. Psi of v and w to be v and w minus s of v. This subtracts the s contribution from the last n minus r components, leaving the first r components unchanged. Compute psi composed with f composed with phi inverse of x and y. F composed with phi inverse gives x and s of x. Then psi sends x and s of x to x and s of x minus s of x, which is x and 0. This is the canonical form stated in the theorem. The map psi is a diffeomorphism. Its inverse sends s and t to s and t plus s of s, which is smooth. The rank theorem is proved. Every smooth map of constant rank R is, in suitable coordinates, the standard projection onto the first R components. The level sets of a constant rank map are therefore coordinate slices, which is the content of the constant rank level set theorem. After the domain straightening of step 2, the Jacobian of f composed with phi inverse has a specific block structure. The upper left r by r block is the identity I sub r because the domain coordinate change was constructed to make the first r components of f composed with phi inverse equal to the identity. The lower right block is the partial derivative of r tilde with respect to y, which a priori could be non-zero. The first r columns of the Jacobian are the columns of the identity block I sub r together with the x partial derivative columns below it. These first r columns are linearly independent, the I sub R block ensures they contain the standard basis vectors of RR as their upper R components. Their joint rank contribution is exactly R. The rank budget is exactly R because the constant rank hypothesis requires the Jacobian to have rank R everywhere on the domain. The first R columns have already consumed the entire budget. They account for all R units of rank. Any additional linearly independent column would push the rank above R, violating the constant rank condition. The last minus R columns correspond to the partial derivatives of R tilde with respect to Y. For the rank to remain exactly R throughout the cube, U tilde 0, not drop, not exceed, these columns must lie in the span of the first R columns. But the first R columns already span all of RR in their upper R rows. The only way the last M minus R columns can lie in that span without increasing the rank is for their lower N minus R rows, the dy R tilde entries, to be 0. The block collapses to 0. The partial derivative of R tilde with respect to Y vanishes identically on U tilde 0. Step 3's conclusion, reached here purely by counting rank against the budget. 0 Y gradient on the cube, whose vertical slices are connected segments, makes R tilde a function of x alone. R tilde of x and y equals S of x. This Y independence is what lets step 4's codomain straightening be defined purely in terms of x. The inverse function theorem extends to smooth manifolds by reducing to the Euclidean version via charts. The statement is the same. If the differential df at a point P is an isomorphism between the tangent spaces T sub Pm and T sub f of Pn, then f is locally a diffeomorphism near P. Invertibility of df at P forces the dimension of M to equal the dimension of N, since an isomorphism requires equal dimensions. The proof works by choosing smooth charts centered at P and at f of P, writing the local coordinate representation f tilde as psi composed with f, composed with vi inverse. The derivative of f tilde at 0 is the composition of the derivative of psi at f of P, the differential df at P, and the derivative of phi inverse at 0. Each of these three linear maps is invertible. The chart maps are diffeomorphisms, so their derivatives are invertible, and df at P is invertible by hypothesis. A composition of invertible linear maps is invertible. The Euclidean inverse function theorem then gives connected open neighborhoods in coordinate space on which f tilde is a diffeomorphism. Pulling back through the charts gives the required neighborhoods U0 and V0 in M and N. The global rank theorem converts topological assumptions about f, surjectivity, injectivity, or bijectivity into differential conclusions about its rank. The theorem says that for a smooth map of constant rank, these topological properties force the rank to be maximal in the appropriate sense. For part A, suppose the constant rank R is strictly less than the dimension of N. By the rank theorem, around any point P, there are charts in which the image of a coordinate ball around P lies in the coordinate slice where the last n-r coordinates are 0. This slice is a closed proper subset of the codomain chart. The image of the closed coordinate ball is compact, being the continuous image of a compact set and contained in this proper closed subset, so it is nowhere dense in N. Cover M by a countable collection of such closed coordinate balls, which is possible since M is second countable. The image f of M is the countable union of the images of these balls, each nowhere dense. The bare category theorem, which states that a complete metric space is not a countable union of nowhere dense sets, then implies that f of M has empty interior. In particular, f of M cannot equal all of N, contradicting surjectivity. By contrapositive, surjectivity forces R to equal the dimension of N. For part B, if R is strictly less than the dimension of M, the canonical form gives coordinates in which f of x and 0 equals f of x and epsilon for small non-zero epsilon. These are two distinct domain points with the same image, contradicting injectivity. By contrapositive, injectivity forces R to equal the dimension of M. For part C, bijectivity means f is both surjective and injective, so R equals both the dimension of N and the dimension of M, meaning these dimensions are equal and R equals that common value. At every point, df is an isomorphism between equal dimensional tangent spaces, so the inverse function theorem for manifolds makes f a local diffeomorphism, a map that is simultaneously bijective, and a local diffeomorphism is a global diffeomorphism, because the global inverse is locally smooth everywhere. A level set of a smooth map Phi from M to N at a value C is the preimage phi inverse of C, the set of all points in M mapping to C. A point P in M is a regular point of phi if the differential d phi at P is surjective as a linear map from the tangent space of M at P to the tangent space of N at phi of P. If d phi at P fails to be surjective, P is a critical point. A value C is a regular value if every point of its preimage is a regular point. The surjectivity condition holds throughout the level set. If the preimage is empty, C is vacuously a regular value. The set of regular points is open in M. The reason is that rank is lower semi-continuous. The rank of the Jacobian at P is determined by the size of the largest non-zero minor. Each minor is a polynomial, hence continuous function of the entries of the Jacobian, which vary continuously with P. If a certain minor is non-zero at P, it remains non-zero in a neighborhood of P, so the rank does not drop below its value at P on a neighborhood. Wherever d phi is surjective, meaning the rank equals the dimension of N, it stays surjective nearby. This openness is used in the proof of the regular level set theorem to restrict phi to an open submersive neighborhood of the level set. The constant rank level set theorem is the direct geometric consequence of the rank theorem for level sets. If phi has constant rank R globally, then every level set is a properly embedded submanifold of codimension R. The codimension R is exactly the number of independent equations that the level set condition imposes. Since d phi has an R-dimensional image, the level set is cut out by R-independent constraints. Fix any C in N and let S be its preimage. For any P in S, the rank theorem provides smooth charts for M centered at P and for N centered at C, in which the coordinate representation of phi is the standard projection. The first R coordinates are projected out and the rest are sent to 0. In these coordinates, C corresponds to 0 in Rn. The level set S intersected with the chart domain is therefore the set where all of x1 through xr are 0, a coordinate slice of codimension R. This is the local slice condition for an embedded submanifold of codimension R. Since P was arbitrary, S satisfies the local slice condition at every one of its points, so S is an embedded submanifold. Properness means the inclusion of S into M is a proper map, equivalently, that S is closed in M. It follows because the single point C is closed in N, and the preimage of a closed set under a continuous map is closed. The constant rank level set theorem says that in the canonical coordinates provided by the rank theorem, every level set is literally a coordinate slice. Two coordinate charts appear, the domain chart U with coordinates x1 and x2, and the codomain chart V with coordinates v1 and v2. In these charts, the map phi composed with the relevant diffeomorphisms has the canonical projection form. In the canonical coordinates, the map sends x1 and x2 to x1 and 0. The first coordinate x1 is projected to v1 unchanged, and the second coordinate x2 is killed, sent to 0. In the codomain chart, only the horizontal axis v1 carries the image of phi. The v2 component is identically 0 for all points in the image. For this example, with rank R equal to 1, the image of the domain is the v1 axis. The level set phi inverse of C in these canonical coordinates is the set where x1 equals 0, the vertical axis of the domain chart. The projection sends x1 and x2 to x1 and 0. For this to equal C and 0, 1 needs x1 equal to C. After shifting coordinates so C equals 0, the level set is exactly the coordinate slice where x1 equals 0. This is the local slice condition that defines an embedded submanifold of codimension R, and here R equals 1, so codimension 1. The slice x1 equals 0 is parameterized by the remaining coordinate x2, which varies freely. In this two-dimensional example with m equal to 2 and r equal to 1, the dimension of the level set is m minus r equals 2 minus 1 equals 1. The 5 dots sample points along the slice at different x2 values. In the general case with m domain dimensions and rank R, the level set has dimension m minus r, parameterized by the remaining m minus r free coordinates. This slice picture is the local slice condition, the defining property of an embedded codimension R submanifold. The theorem establishes it at every point of the level set by the same chart construction. Properness was checked on the previous slide. When the constant rank hypothesis is strengthened to full surjectivity of the differential, that is, when phi is a smooth submersion, the constant rank level set theorem specializes to a particularly clean statement, A submersion has constant rank equal to the dimension of n by definition. The level sets are therefore properly embedded submanifolds of codimension equal to the dimension of n, and their dimension is the dimension of m minus the dimension of n. The proof is a single sentence. Apply the preceding theorem with R equal to the dimension of n. A smooth submersion has constant rank equal to the dimension of n by definition. Surjectivity of the differential at every point is the condition that the rank equals the dimension of the target. Applying the constant rank level set theorem with R equal to the dimension of n gives that every level set is a properly embedded submanifold of codimension equal to the dimension of n. The submersion condition requires the dimension of m to be at least the dimension of n, since the differential from t sub pm to t sub phi of pn can only be surjective if the domain dimension is at least the codomain dimension. With codimension equal to the dimension of n, the dimension of each level set is the dimension of m minus the dimension of n. The regular level set theorem is the principal geometric form of the implicit function theorem. Unlike the constant rank level set theorem, it requires no global rank condition on all of m, only a surjectivity condition on the level set of interest. The hypothesis is that C is a regular value. Every point of phi inverse of C is a regular point, meaning d phi is surjective there. The conclusion is that phi inverse of C is a properly embedded submanifold of M with codimension equal to the dimension of n. The proof reduces to the submersion case by restricting the domain. Define the open set U as the set of all points P in M, where d phi at P has rank equal to the dimension of n, the set of regular points. This set is open by lower semi-continuity of rank. Since C is a regular value, every point of phi inverse of C belongs to U, so the level set sits entirely within U. The restriction of phi to U is now a smooth submersion. D phi is surjective at every point of U by construction. The submersion level set theorem then says that the preimage of C under this restriction is a properly embedded submanifold of U of codimension equal to the dimension of n. Since U is an open submanifold of M, the inclusion of U into M is itself a smooth embedding. Composing the embedding of phi inverse of C into U with the embedding of U into M then gives a smooth embedding of phi inverse of C into M. Closeness in M follows from continuity of phi and closeness of the single point C. The regular level set theorem's proof constructs a specific open subset of M on which phi restricts to a submersion. The ambient manifold M is depicted as the large rectangle. The level set phi inverse of C and the critical points of phi are distributed across M, and the task is to separate them by an open set. The level set phi inverse of C is a smooth curve inside M. At every point of this curve, the differential d phi is surjective. The regularity hypothesis asserts this. The level set itself is smoothed by the regular level set theorem, whose proof we are now illustrating. Critical points, where the rank of d phi is strictly less than the dimension of n, appear elsewhere in M, but not on the level set phi inverse of C, because C is a regular value. The separation between the level set and the critical points is the structural fact exploited in the proof. The set of regular points is open, so the level set, being entirely regular, is surrounded by an open neighborhood of regular points. The open set U is defined as the set of all points in M where d phi has rank equal to the dimension of n. Because rank is lower semi-continuous, the rank of a matrix cannot drop below its value at a given point on any open neighborhood of that point. U is open. Since every point of phi inverse of C is regular, the level set is contained in U. The restriction of phi to U is a smooth submersion. At every point of U, the differential is surjective by definition of U. The critical points shown in red lie outside U. The inclusion chain shows the embedding structure. Phi inverse of C embeds into U as a properly embedded submanifold. This follows from the submersion level set theorem applied to the submersion phi restricted to U. The open embedding of U into M then gives an embedding of phi inverse of C into M. Closeness of phi inverse of C in M, the properness condition, follows from continuity of phi and the fact that the single point C is closed in N. The inset shows what happens when C is a critical value, when some point of phi inverse of C is a critical point with rank less than the dimension of N. The level set can develop a cusp singularity, a point where the curve is not locally a manifold. The cusp parameterized by t to t squared and t cubed is the standard example, the level curve of y squared minus x cubed at the critical value 0. At the cusp point, no neighborhood of the singular point in the level set is diffeomorphic to an interval, so the level set fails to be a submanifold there. The regularity hypothesis is what excludes this failure. The regular level set theorem gives a sufficient condition for a level set to be an embedded submanifold. The characterization proposition says this is also necessary. A subset S of M is an embedded K submanifold if and only if the following holds. Every point of S has a neighborhood U in M such that S intersected with U is a regular level set of a smooth submersion from U to R M minus K. The necessity direction uses the existence of slice coordinates for embedded submanifolds. In slice coordinates, S is the zero set of the last M minus K coordinate functions, and those functions form a smooth submersion. The sufficiency direction is exactly the submersion level set theorem. A defining map for S is any smooth map phi from M to some manifold N for which S is a regular level set of phi. When the codomain is Rm minus K, the map is called a defining function. The characterization proposition says that defining maps always exist locally around any point of an embedded submanifold. They are the standard certificate of embeddedness in the category of smooth manifolds, and they provide the framework in which the implicit function theorem operates geometrically. The standard n-sphere Sn is defined as the set of unit vectors in Rn plus 1. To apply the regular level set theorem, define f from Rn plus 1 to R by
f of x equals the squared norm of x, the sum of the squares of all n plus 1 coordinates. Then Sn equals f inverse of 1.
The differential of f at x is the linear map from Rn plus 1 to R, sending a tangent vector v to 2 times the sum of xi vi over all I. This is the dot product of x with v scaled by 2. A linear map from Rn plus 1 to R is surjective if and only if it is not the zero map. The differential df at x is 0 exactly when x is the zero vector. The inner product of x with every v is 0 only if x itself is 0. Since every point of Sn has squared norm 1 and is therefore non-zero, the differential is surjective at every point of Sn. Hence, 1 is a regular value of f. The regular level set theorem then gives the conclusion. Sn is a properly embedded submanifold of Rn plus 1 with codimension 1, hence dimension n. The defining function for Sn is simply the squared norm function f, and the submersion condition is satisfied everywhere on Sn. The sphere example just computed, drawn for n equal to 1, the unit circle as the level set of the squared norm, with the origin, the gradients only 0, sitting at the center. 6 sample points, x sub 1 through x sub 6, are placed at regular angles on the circle. Each has squared norm equal to 1, they all lie on S1. The gradient of f at each of these points is the vector 2x sub k, which points radially outward from the origin. The gradient arrows point radially outward, each of norm exactly 2, visibly non-zero at every sample point. That non-vanishing is the surjectivity of df checked on the previous slide, now seen all around the circle at once. The one critical point of f, the origin, glows red. Its f value is 0, not 1, so it misses the level set entirely. The dashed gap makes the separation visible. The only critical point sits strictly inside the circle, at positive distance from it. That separation is the geometric reason 1 is a regular value. The regular level set theorem then applies as on the previous slide, making Sn a properly embedded submanifold of dimension n. The orthogonal group O of n is the set of n by n real matrices, A for which A transpose A equals the identity I sub n. Two spaces are needed to apply the regular level set theorem. M of nr is the space of all n by n real matrices, identified with Rn squared. S of n is the space of n by n symmetric matrices, identified with R of dimension n times n plus 1 over 2. Define phi from M of nr to S of n by phi of A equals A transpose A. Then O of n equals phi inverse of I sub n. The differential of phi at the matrix A in the direction B is computed by differentiating phi of A plus TB with respect to T at T equals 0. The result is B transpose A plus A transpose B. This map from M of nr to S of n is linear in B. To check surjectivity at any matrix A in O of n, given an arbitrary symmetric matrix C, we need to find B with d phi at the matrix A applied to B equaling C, set B equal to 1/2 times A times C, then B transpose A plus A transpose B equals 1/2 times C transpose times A transpose A plus 1/2 times A transpose A times C. Since A is orthogonal, A transpose A equals I sub n, so this simplifies to 1/2 C transpose plus 1/2 C. Since C is symmetric, C transpose equals C, giving 1/2 C plus 1/2 C equals C. The differential d phi at A is surjective at every point of O of n, so I sub n is a regular value. The regular level set theorem then makes O of n a properly embedded submanifold of M of nR. Its codimension equals the dimension of S of n, which is n times n plus 1 over 2. Its dimension is n squared minus n times n plus 1 over 2, which simplifies to n times n minus 1 over 2. For example, O of 2 has dimension 1. It is a disjoint union of two circles, the rotations and the reflections. O of 3 has dimension 3. The one-sheeted hyperboloid S is defined by the equation x squared plus y squared minus z squared equals 1 in R3. Define phi of x and y and z to be x squared plus y squared minus z squared, then S equals phi inverse of 1. The gradient of phi is the vector 2x and 2y and negative 2z. The gradient of phi vanishes only at the origin. 2x equals 0, 2y equals 0, and negative 2z equals 0 simultaneously requires x, y, and z all to be 0. The origin has phi value 0, so it is not in the level set phi inverse of 1. Therefore, the gradient is non-zero everywhere on S. The differential d phi is then surjective throughout S, and 1 is a regular value. The regular level set theorem gives that S is a properly embedded two-dimensional submanifold of R3, the one-sheeted hyperboloid. The classical implicit function theorem gives additional information near any specific point. At the point 1 and 0 and 0, the partial derivative of phi with respect to x is 2, which is non-zero. Apply the implicit function theorem with x as the implicitly defined variable and y and z as the free parameters. It yields a smooth function f of y and z, defined near the origin in R2, such that phi of f of y and z equals 1 throughout a neighborhood. Solving explicitly by choosing the positive branch of the square root, f of y and z equals the square root of 1 plus z squared minus y squared. This is smooth near the origin where the argument of the square root is near 1 and hence positive. The summary table collects the governing data for each result in the logical hierarchy. The inverse function theorem in Euclidean n-space concerns a smooth self-map with an invertible Jacobian at a point and concludes that f is a local diffeomorphism at that point. The differential condition is both necessary and sufficient for local invertibility. The implicit function theorem concerns a smooth map from Rn plus k to Rk with the k by ky partial derivative matrix non-singular at a base point. The conclusion is that the level set is locally the graph of a smooth function, a purely local result about solving an implicit equation for the y variables in terms of the x variables. The rank theorem operates on smooth maps of constant rank R between manifolds of dimensions m and n. Its conclusion is a canonical form. In suitable smooth charts at any point, the map is exactly the standard projection sending x and y in RR times Rm minus R to x and 0 in RR times Rn minus R. This is the nonlinear analog of the row reduction canonical form for linear maps. The constant rank level set theorem, which follows directly from the rank theorem, says that under the same constant rank hypothesis, every level set is a properly embedded submanifold of dimension m minus R. The codimension R is the number of independent constraints imposed by the level set condition, matching the dimension of the image of the differential. The regular level set theorem begins by supposing C is a regular value of phi, meaning d phi is surjective at every point of the level set. Then phi inverse of C is a properly embedded submanifold with codimension equal to the dimension of the codomain n. This is the statement that captures, in full geometric generality, the content of the implicit function theorem for smooth manifolds. The logical chain from the contraction lemma to this final theorem is the complete argument.